So we've got this differential equation. It's linear, homogeneous, constant coefficients. So what's our usual technique for solving that? Like without even knowing anything else about it, what would be a good guess for what the solution should look like?
Would it be like the C1 e to the t and plus C2 e to the minus t kind of setup?
Yeah, although we don't yet know whether it's going to be exactly 1t or negative 1t or whatever t. So we're just going to guess e to the something t. So our usual guess, anytime you've got a second order or really any order differential equation, as long as it's linear, homogeneous, and has constant coefficients, like in this case, the coefficients are just 1, -1, and 1/4, then the guess e to the RT should always work. It might lead to some other complications, but you can always start by guessing e to the RT. The tricky part, of course, is knowing what R is going to be. But if we plug that in, what's going to happen to y prime, for instance, and y double prime? What would those be? Like if you just take the derivative of e to the RT, what do you get?
R to the R times e to the RT.
Yeah. And then take the derivative again, what does that become?
R squared e to the RT.
Yeah. So if we substitute those in, we get R squared e to the RT, R e to the RT, and e to the RT. And then, of course, with the rest of the equation, y double prime minus y prime plus 1/4 y equals 0. And since e to the RT shows up in every term, what can we do with that? Yeah, we can factor out e to the RT. If we factor out the e to the RT, then we're left with just R squared minus R plus 1/4. In other words, a quadratic. So this would be the characteristic quadratic of this differential equation. If we can find R values that make the quadratic 0, then we know the R values that are going to work in this guess. So how would we find R values that work here? Does this quadratic factor easily?
Is it R minus half squared?
R minus 1/2 times itself should work here, because the negative 1/2 times negative half gives us positive 1/4, and negative 1/2 R plus negative 1/2 R gives us negative 1 R. So that means the only R value we get is positive 1/2. So we do have a repeated root situation here. And the terminology we usually use there is that this root has a multiplicity 2, in the sense that it shows up twice when you factor it. So that means e to the 1/2 t should be a solution. We now know R, so we can say for certain that e to the 1/2 t is a solution. So we'll say y1 is e to the 1/2 t. But we need a y2. We can't just have another copy of e to the 1/2 t. So what would you expect the second solution to look like?
Could it be a negative half t or?
Negative 1/2 is not one of the roots though, so negative 1/2 won't work. But how can we modify e to the 1/2 t to get another function that is still a solution, but doesn't count as just a copy of the same solution? The derivative would just give us 1/2 e to the 1/2 t, which is not going to be a solution either in this case, or which is I mean, that is a solution, but it's just another copy of the other one. 1/2 times e to the 1/2 t is just a scalar multiplier times the original solution. So to get a second solution, let's explore this idea of reduction of order as a method to doing this. The general idea of reduction of order is that if you have a solution of a differential equation, you can, or specifically second order, if you have a solution of a second order equation, you can find the other solution, the other independent solution, by making a different sort of guess. In particular, we already know that y equals e to the 1/2 t is a solution. What we're going to do is we're going to guess, let me label this. This method is called reduction of order. And I think it'll become apparent why in a moment. Reduction of order. The idea is if we already have y1, we're going to make the guess that y2 equals y1 times some unknown function, let's say v. And we're treating v as some unknown function of t. We just don't know what function yet. If we can find a function that makes this true, then that means that we'll have y2. But this is the guess we're going to use, because if we actually take that guess and plug it in, of course, we'll need to find y prime and y double prime. What would y2 prime look like if y2 is defined as this product of y1 and v? How would you write out the derivative of this product?
Would it be 1/2 e to the half t?
Well, ignoring the 1/2 e to the e to the 1/2 t is going to, that y1 prime is definitely going to be 1/2 e to the 1/2 t. But the problem is this isn't just y1, it's y1 times some other function. How do you usually take the derivative of a function times a function?
Oh, then product rule.
Yeah, we're going to need to use the product rule here. So we'll have derivative of the first thing times the second thing as is, plus the first thing as is times derivative of the second thing. So that's the first derivative of our new guess, y2 prime. And then we'll also need the second derivative, which means we'll need to use the product rule again. And of course, we'll eventually be replacing every y1 with e to the 1/2 t and every y1 prime with 1/2 e to the 1/2 t. But I'm just going to leave it as y1 and y1 prime for now. We can fill the details in later. But now we want to take the derivative again, which means we'll need to apply the product rule once more to each of these individually, or I guess twice more then. So what would the derivative of y1 prime times v look like? How would that expand?
Y1 double prime vt or v plus v prime y1 prime?
Yeah. Because again, we're just taking derivative of the first thing times the second thing as is, and then the first thing exactly as is plus the derivative of the second thing. And then what about the y1 v prime? What would that derivative look like?
Y1 prime v prime t plus y1 v double prime t?
Yeah. And note that we've got now two copies of this same y1 prime v prime. So we can just combine like terms and call that 2 y1 prime v prime. Let me clear that up a little bit. And this is actually as far as we're going to need to go for this one, because we now have a second derivative. But I'm going to take this one step further, because something really interesting appears if we take the third derivative and beyond. If we look into y2 triple prime, y1 double prime times v is going to turn into what? What would that look like under the product rule?
Would it be like y1 triple prime v plus y1 double prime v prime?
Right. And then the 2y1 prime v prime is going to become
2y1 double prime v times v prime plus v double prime plus v2 v double prime y1 prime.
Yeah. And note that these are like terms, so those are going to combine. And then the last term, y1 v double prime is going to become
y1 prime times v double prime plus y1 times v triple prime.
Yeah. And again, these are like terms, so those are going to combine. So we end up with, if we combine these, we've got 3 copies of y1 double prime v prime, because we've got 1 plus 2 more. And likewise, 3 copies of y1 prime v double prime. So putting that all together, and then 3 copies of this one, and 1 copy of this one. Do you see any pattern in these coefficients here? If we've got 1, 1, 1, 2, 1, 1, 3, 3, 1, have you seen those numbers in combination before?
Is it like Pascal's triangle?
Yeah, this builds up to Pascal's triangle as the coefficients in the exact same way that binomial expansion does. For instance, if you were raising a plus b to the 3rd power, you'd end up with coefficients 1, 3, 3, 1, and the terms 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed in very much the same way as we have here. It's just that instead of powers on the exponent, or instead of exponents on the variables, we've got derivatives on the functions. So the product rule for derivatives ends up following the exact same pattern as binomial expansion if you take it out to 2nd derivative, 3rd derivative, 4th derivative, and so on. You've got every possible combination of derivatives of the 2 functions, and the coefficients end up just being the numbers from Pascal's triangle again. Because that's ultimately what we're doing. We got this 3 from adding 2 from this one plus 1 from this one. If we took this out to another step, we'd have a 4 from this one combined with these 3, and a 6 from these 3 combined with these 3. So these are combining. When we take derivatives, the different terms combine with each other in a way that exactly mimics the add these 2 numbers to get this number pattern of Pascal's triangle. So this naturally leads to essentially an equivalent of the binomial expansion theorem for the product rule. So this is a very useful shortcut if you have to take higher derivatives of a product of functions. If you've got like a function times a function and you have to take its 5th derivative, you can do that very quickly just by looking to the 5th row of Pascal's triangle to get the coefficients, and then look at all possible combinations of derivatives. So like y, 5th derivative of y times v, 4th derivative of y times 1st derivative of v, and so on. Very useful shortcut. In this case, of course, we only need to take it up to the 2nd derivative, but I think this is a very useful pattern to know if you need to take any higher derivatives of products of functions. Any questions on that so far? So let's try actually plugging this in. And remember, our goal here was to just find some function we can multiply by y1 to get another function, y2, that works. So that means, of course, we'll need to plug these in to the original differential equation and see how that works out. So let's try that. If we just write out y2 double prime, so this whole thing, and then we've got minus y prime, which is just the 1st derivative. And then 1/4 times y itself. And we want to require that that equals 0. We now have an equation we can solve for v. And of course, there's also y1 here, but we know what y1 is, so we can fill in y1 later if we need to. But let's see if we can simplify this first. What do we have first? What do you think would be some good ways of combining terms here? What would be some terms that would be useful to put together? If we wanted to rearrange these terms to have some nice, neat combinations of terms. What are we trying to solve for here? What's our actual goal?
We're trying to solve for y2, I think, right?
Eventually we want y2, yeah. But we know y2, or we're assuming y2 is y1, which we know, times some unknown function v. So if we can figure out what v is, we just multiply that by the y1 we already have, and we get y2. So if we're trying to find v here, we may as well treat this as a differential equation with v as the unknown, and split up the terms based on the derivatives of v. If we can write this as something times v double prime plus something times v prime plus something times v equals 0, we'll have a differential equation in terms of v that we might be able to solve. So let's group these together by order, by derivatives of v. For instance, if we look for v double prime, it looks like this is the only v double prime term in the whole thing. So we've got y1 times v double prime. And then if we take a look for all of the v single prime, looks like we've got this one. So 2y1 prime, and this one. So 2y1 prime minus y1 times v prime, because we can factor the v prime out of both of those. And then if we take a look at the other terms, we have y1 double prime times v minus y1 prime times v. And I'm preemptively factoring the v out of all of these, plus 1/4 y1 times v. So we're just factoring a v out of these three terms. And we can now say that these y1, so something v double prime plus something v prime plus something v equals 0. So we now have a differential equation in terms of v that we might be able to solve. And this is a slight problem because the coefficients are not constants. And we don't really know a good method yet of solving a second order differential equation where the coefficients are not constants. The coefficients themselves are functions of t. But something very useful we can do here. What do you notice about this coefficient in particular? This y double prime minus y prime plus 1/4 y. Where have we just seen that?
At the top differential equation?
Yeah, that's the original, or at least the left side of the original differential equation. So if y1 is a solution of the original differential equation, that means that y1 has to make this expression equal 0. In other words, this entire coefficient is going to have to be 0. And you can check that as well. If you actually take the e to the 1/2 t, plug it in here, and then 1/2 e to the 1/2 t and 1/4 e to the 1/2 t, they should all cancel out. But we know in advance that it's going to cancel out because this is just the left side of the original homogeneous differential equation. So any solution is going to make this thing 0. Which means if this is gone, we really just have a v prime term and a v double prime term. And that's actually very convenient. Because if we have, let me put this off to the side. If we have, let me just call this A and B. So we've got A v double prime plus B v prime. What's the order, and then the v term dropped out. What's the order of this equation? That is, what's the highest derivative that shows up in it?
Would it be 2?
Yeah, this is definitely a second order differential equation. But we can modify it to make it only first order. This is really why we call this approach reduction of order in the first place. This assumption is useful specifically because it makes this v term completely drop out. without the v term, if we only have v prime and v double prime, we can make a very useful substitution. We can say, let's make up a new variable. I'm going to call this w. So it's equal to v prime. So we're replacing every v prime with w. But if v prime is defined as w, what's v double prime going to be?
W prime?
Yeah, so v double prime can be replaced with the first derivative of w. And now what's the order of this equation?
First order.
Right, this is first order. And moreover, it's first order and separable. We can just move the terms around, subtract bw from both sides, divide both sides by w, multiply both sides by dt, and now we have a differential equation, and we can that we can just integrate on both sides. So this is really why this is called reduction of order in the first place. By making this guess, we can force the v term to cancel out completely. That means that this second order equation that's missing a plus something v term can be rewritten as a first order equation using this substitution by treating v prime as a new variable. Then you can solve that equation for w using separation of variables, or integrating factors would also work because it's linear, but separation of variables would be a lot easier, I think. So solve this by separating the variables and integrating. That gives you a value for w. Once you've got w, how do you get back to v? If we were defining w as the derivative of v, then how would you get back to v if you already know w?
We integrate?
Yeah, once you find w from solving this equation, you can integrate to find v. And once you know v, you multiply that by the solution you already have to get a second solution. So this is the key idea of reduction of order. By making this guess as our second solution, just some multiplier times the solution we already have, you can force the v term to cancel out, so you have a new second order differential equation that you can turn into first order by making this exact substitution. Solve that first order equation for w, integrate to turn it back into a solution for v, and then multiply that v solution times your original solution y1 to get a y2 second solution. And that should end up being a genuinely different type of solution because it's not just a constant times y1, it's a new variable times y1, a new function times y1. Any questions on that general reduction of order approach so far?
How would we know to use that, to start using this approach? Like
in general, this approach works anytime you have a second order linear differential equation and you know one solution, and you know there's got to be some second solution, but you don't know what it is yet.
Okay.
And this is mostly useful in part to figure out how to deal with this repeated root situation. If you only have one root to the characteristic quadratic, we can use this to find the second solution. But also more generally, if you're dealing with a second order linear differential equation with non-constant coefficients, like let's say you had something like, I don't know, t squared y double prime minus 5t y prime plus 3y equals 0. These are non-constant coefficients, which means guessing e to the RT won't work at all. But if you already have a solution, like maybe one of the solutions is given, or maybe you just try out various functions as guesses and you finally find one that works. As long as you have a solution that works, you can use reduction of order to find the other solution, the second independent solution, to form a fundamental set of two solutions. And then the general solution will just be linear combinations of those.
Okay.
So that's really the main use of reduction of order, or at least one of the main uses, being able to find the second solution of a linear second order equation if you already know one of the solutions. So let's see if we can apply that to this specific case, because we kind of generalized this. We've been looking at this in general if you end up with something v double prime plus something v prime, but we know what those somethings are. We have the coefficient of v double prime, we have the coefficient of v prime. So let's actually fill those in. For example, we've got a y1 here. We know y1 is just e to the 1/2 t. So let's go ahead and fill that in. And this y1 we can fill in with e to the 1/2 t. But what's y1 prime going to be?
Would be half e to the half t.
Yeah, so if we fill that in, what does this simplify to?
It would be 0 then.
Yeah. So in this case, we get this rather unusual situation where the v prime term also turns into 0. And it turns out that's actually always going to happen if you have a characteristic quadratic that turns into a repeated root. Anytime you've got constant coefficients that lead to a characteristic quadratic with a repeated factor. So if you only get one solution because your characteristic quadratic has a repeated root, then in cases like that, the v term certainly cancels out. The v prime term, it turns out, also cancels. So all that's left is the v double prime term. So if we write that out, we now have, just looking at this, we now know that e to the 1/2 t times v double prime must equal 0. So how can we solve that for v double prime?
You would have to integrate twice.
Right. And of course, we'll probably want to get rid of this e to the 1/2 t first, but we can just divide both sides by e to the 1/2 t, because that's never 0. These cancel out, we just get v double prime equals 0. So let's go with that. We know v double prime is 0. That's the overall result of all this stuff with these substitutions. V double prime equals 0. We can get rid of one of those derivatives by integrating. What do you get if you integrate 0 dt?
Just constant?
Yeah. I'm going to call that C1 because we're going to need to have some different C values as well. Because our next step is going to be to integrate again. What do you get if you integrate C1?
It should be C1t plus the C2?
Yeah. Actually, let me call the first one C2, because I think we're going to be wanting C1 as a coefficient for Y1 anyway. So let's say C2t plus C3. So that is our solution for V. All this work leads to the fact that V double prime must equal 0. And the only type of function whose second derivative is 0 is a linear function. So this is really the overall result here, that V has to be a linear function, something t plus something. But what was our intention for V in the first place? Why do we need to find this function V anyway? What are we going to do with it now that we have it?
Multiply it by y1 to get y2.
Yeah, exactly. We want to find y2, and we were assuming from the start that y2 is V times y1. So we plug V in here, and let's see what we get. Y1 was e to the 1/2 t. We're multiplying that by C2t plus C3. So we get C2t e to the 1/2 t plus C3 e to the 1/2 t. So we could say this is our y2. However, we don't really need all possible solutions. We just need a solution. We need a function to call y2. And what's the only piece of that that's really new? What was the solution we already had here?
E to the half t.
Yeah, we already have e to the 1/2 t as y1. So we don't really need plus a constant times e to the 1/2 t. We're going to have a constant times e to the 1/2 t from y1 anyway. So the only part of this we really need is this genuinely new type of function, t e to the 1/2 t. That's the new part of this. So let's call that y2. And we now have two genuinely different solutions. E to the 1/2 t, which we got from the characteristic quadratic, and t e to the 1/2 t, which we got from reduction of order. However, you don't really have to go through this process every single time. You should get the exact same result anytime you have a constant coefficient linear differential equation with a characteristic quadratic that has a repeated root. One of the solutions will be e to the rt. The other solution, you can't just have another copy of e to the rt. Instead, you have t e to the rt. And in fact, this idea of an extra times t ends up being useful in a lot of other situations as well. In general, anytime you need to make a guess for some sort of solution, but the guess you would naturally make is already a homogeneous solution, usually you can try multiplying that solution by t and see if that also works as a new solution. So if the solution you would be guessing is already in use, try multiplying it by t and see if that works. That's often a good next guess to use if what you would usually guess doesn't work. Any questions on that so far?
Kind of just to make sure for using this method, we had to make sure this the differential equation is also second order linear homogeneous and only has one root, or
specifically if the characteristic quadratic you would make has only one root, then one of the solutions is e to the power of that root times t as usual. The other solution, because we do need a second solution, is going to be t times e to the rt. And this actually expands to higher order equations as well. Like let's say you've got a third order differential equation, then you're going to have a characteristic cubic, which could have up to 3 roots. But let's say your characteristic cubic factors to just like y plus 2 to the third power. Then e to the negative 2t is a solution. You don't have any more roots, so you can't just have another copy of e to the negative 2t, but you could have t e to the negative 2t. And it turns out the third solution is going to be t squared e to the negative 2t. You just keep tacking on an extra times t to get more solutions. So this approach generally works in any situation where you've got repeated roots. If you have only one solution that you can find and you need another solution, as long as it's linear with constant coefficients, then the other solution is going to be the solution you already have times t. If the coefficients are not constant, then it's not just going to be times t, but you can still use the overall approach of reduction of order to turn the second order equation into a first order equation. And again, this is why it's called reduction of order. We are literally reducing the order of the equation from second order to first order. And using this, we can now write out our general solution. The general solution here is going to be just linear combinations of these. C1 times Y1 plus C2 times Y2. So there's our general solution. And note that this is why we didn't really need to include plus C3 e to the t in our Y2, because C3 e to the 1/2 t is just duplicating what we already have from Y1, C1 e to the 1/2 t. We don't need another copy of that. So that's our general solution. And now that we have the general solution, how would we find the specific solution?
We'll plug in our initial condition.
Yeah, using the initial conditions. For example, we know that y of 0 must be 2. So we can say if we plug in 0 for t, that must equal 2. And then for the rest of the initial conditions, we'll need to take the derivative. Y prime equals, so when we take the derivative, e to the 1/2 t just becomes 1/2 e to the 1/2 t. But for this one, we're going to need the product rule. We get C2 times derivative of t is 1 times e to the 1/2 t exactly as it is, plus t exactly as it is times derivative of e to the 1/2 t. So that'll be t times 1/2 times e to the 1/2 t. So there's the derivative based on using the product rule for t e to the 1/2 t. And we can now plug in the other piece of information here. We know that if we write out this derivative using 0 for t, we get c1 times 1/2 times e to the 0 plus c2 times e to the 0, which is 1, plus t over 2, so 0 over 2 times e to the 0. And that has to add up to b. So let's simplify this. First equation, e to the 0 is just 1. So let's go ahead and fill that in. That's 1 for all these. So what does this equation tell us?
We can find C2 with that, or?
Not C2 though, because C2 is getting multiplied by 0. So what happens to this entire term?
Oh, that will become 0.
Yeah, that whole thing is 0. So we really just have, all that's left is C1 equals 2. So this actually tells us the value of C1. If we simplify the other equation though, we get B equals C1 times 1/2 times 1. So 1/2 times C1 plus C2 times 1 plus 0 is just going to be 1. And we also know what C1 is. C1 is 2. So we get B equals 1/2 times 2 plus C2. In other words, C2 is B minus 1. So we now know exactly what C2 is as well in terms of B. So we now have C1 and C2. We should be able to fill those in for C1 and C2 in the original general solution to get the specific solution. Any questions on that so far? So let's try writing that out and see what we get. We now know C1 is 2, so that's 2 e to the 1/2 t. And we know C2 is b minus 1, t e to the 1/2 t. So this is our specific solution in terms of b. And I believe this question was really asking how does the end behavior, the limit as t goes to infinity, how does that depend on b? How does b determine whether it goes to infinity or negative infinity or 0? So we want to figure out what b values make this happen. The left term, the 2 e to the 1/2 t, that's always going to approach what as time goes on?
It will go to positive infinity.
Yeah, this is always going to go to positive infinity no matter what b is. But what about this term? What if b is, for instance, what if b is extremely large positive?
Then it will also go to positive infinity?
Right, so for at least some b values, large positive values, both of these go to positive infinity. But what if b is a very large negative number?
It will go to negative infinity?
Right. If b minus 1 ends up being negative, this term goes to negative infinity. So we have something that turns into positive infinity plus something that turns into negative infinity. For that undetermined form, we want to check which one's growing or shrinking faster. So which one do you think is changing faster, e to the 1/2 t or t e to the 1/2 t?
Would it be t e to the 1/2 t?
Yeah, assuming we're talking about large enough t values, and we are talking about t going to infinity, so t will always eventually get large enough. As long as we're talking about large enough t values, this term is growing or shrinking faster. So that means this term is going to dominate. So we really just need to check what b values make this term go to positive infinity versus negative infinity. You can also kind of see this by factoring the e to the 1/2 t out of both sides, or out of both terms. You could say y equals e to the 1/2 t times 2 plus b minus 1t. Assuming t is positive and getting larger and larger, the end behavior of e to the 1/2 t depends on whether this whole thing is positive or negative. So what's the breakpoint on b? What b value is going to lead to this changing to positive versus negative?
Oh, then b equals 1.
Yeah, if b is exactly 1. If b is greater than 1, then this is going to become positive, so the whole thing goes to positive infinity. If b is anything less than 1, this becomes negative, so the whole thing goes to negative infinity. What if b happens to be exactly 1?
1 is still go to positive infinity?
Yeah, because if b is exactly 1, this term drops out, but the rest of it, 2 e to the 1/2 t, definitely goes to positive infinity. So that's how we can describe how we can categorize the end behavior here. The end behavior definitely depends on the value of b. B equals 1 is the breakpoint. Any b value higher than that, the whole thing goes to positive infinity. Any b value lower than 1, the whole thing goes to negative infinity. And at the borderline, when b is exactly 1, the whole thing still goes to positive infinity. Yeah, exactly. I would say b equals 1 is our critical point or our critical value of b. And then I guess we can specifically say if b is greater than or equal to 1, then y goes to positive infinity. Because or equal to is included, since if b is exactly 1, then what's left does go to positive infinity. And if b is strictly less than 1, not including 1, then y goes to negative infinity. And it looks like there are no b values that lead to finite limits. Everything is going to go to either positive infinity or negative infinity, but which one depends on the value of b. In other words, whether it goes to positive or negative infinity depends on the slope of the graph at t equals 0. Because the whole point of b in the first place was b is the value of y prime. B is how steep the graph is at that initial condition. Any other questions on that? All right, then I will see you next time.
Thank you.
You're welcome.